Envision an immense asteroid hurtling towards Earth. As you observe this movie, is it possible for us to evade a catastrophic event of immense magnitude? Or are we powerless in the face of celestial influences? These critical questions pushed NASA to fly a specially built probe straight into the asteroid's path. However, the outcomes defied expectations. What unforeseen plot developments occurred? What are the ramifications of this for our safety? Join us as we delve into the perplexing phenomenon of an asteroid collision that has left NASA experts astounded and unable to provide a definitive explanation for its occurrence. Prepare for an exploration of the captivating voyage and the unveiling of enigmas beyond the cosmic boundary. Engineers and scientists have devoted their efforts for years to constructing a probe with a specific objective: the purposeful destruction of NASA's Double Asteroid Redirection Test, DART. The purpose was apparent from the start. As it had a short lifespan, the spacecraft was created with the express purpose of assessing a new planetary defense method. It was designed to be a comprehensive solution specifically aimed at two near-Earth objects called Dios and Doros. Dios, a Greek term denoting twin, was detected on April 11, 1996, by researcher Joseph Monani utilizing the Spacewatch telescope at Kitt Peak National Observatory in Tucson, Arizona. Scientists hypothesized that Doros might have a moon after they detected odd echoes in the data from NASA's Goldstone Solar System radar in the Mojave Desert near Barstow, California. They got more certain about it by looking at how bright Doros appeared over time using telescopes. They also analyzed radar photographs taken by the Arecibo Observatory in Puerto Rico on November 23, 2003. As Doros and its moon revolve around the Sun, they get close to Earth's orbit, occasionally coming fairly near to us. In 2003, Doros got as close as 0.048 astronomical units, AU, to Earth. 1 AU is the distance from the Sun to Earth. Although these asteroids don't pose a hazard to Earth, NASA picked them for the special DART mission. It's NASA's first mission to check a new technique to defend our planet. The technique involved the probe's rapid collision somewhat decelerating Doros' orbit, leading to a lasting shift in its trajectory. However, the issue in this planetary defense technique comes not just in manufacturing the probe and colliding it with the asteroid, but in precisely determining the impact intensity. The purpose is to dislodge the asteroid just enough to steer it into a safe orbit. This precision is vital. When discussing asteroid defense, detonating these rocky asteroids may cross one's mind. Planting an explosive charge on an asteroid or deploying it within, analogous to situations in movies like Armageddon, seems theoretically plausible. However, the underlying issue resides in the aftermath of such an explosion. The resulting detonation would spawn several asteroid fragments, each following unpredictable trajectories and potentially posing a renewed threat to Earth. While humans might succumb to such dramatic tactics in grave crises, research advocates a more realistic approach. Instead of devastation, the focus is on moving asteroids out of collision trajectories or tugging them away. Depending on the location and time of danger detection from space, a relatively minimal effort may be sufficient to divert an asteroid into a safe orbit. Yet, the margin for error is tiny, as an insufficient or excessive push might leave the asteroid still posing a hazard. This highlights the necessity of NASA completing the process on Doros, an asteroid positioned sufficiently far away to avoid any potential hazard. Regardless of the test conclusion, the nightmarish scenario of a big asteroid hitting Earth is unsettling. The immediate destruction of the impact zone would be catastrophic, and the entire fabric of society could face a protracted demise due to the aftermath. The effect would be severe tsunamis, flames, atmospheric dust, poison, and unexpected chain reactions from subsequent natural calamities. This series of events replicates the horrific fate the Chicxulub asteroid imposed on the dinosaurs millions of years ago. Imagine a massive asteroid as large as a whole mile coming into Earth at 30,000 miles per hour. The energy it brings is like setting off a huge bomb, a staggering 1 million megatons. To appreciate how devastating this may be, let's consider a lesser version. Imagine an asteroid the size of an ordinary home hitting Earth at the same superfast speed. It would release energy similar to the bomb dropped on Hiroshima, roughly 20 kilotons. Buildings composed of solid concrete within half a mile would be flattened, and wooden structures within a mile and a half could be destroyed. This would do severe damage to any city it hits. Now, think about an asteroid as massive as a 20-story building, each side measuring 200 feet. This space rock could carry as much energy as the biggest nuclear bomb today, between 25 to 50 megatons. If it crashes, it might flatten reinforced concrete buildings within a 5-mile radius. In fact, it might entirely demolish most significant cities in the United States. For a space rock to cause widespread harm on Earth, it must be huge. Scientists think that an asteroid roughly 7 to 8 kilometers broad would do the trick. If such a gigantic asteroid slams into our planet, it will cause a catastrophic series of events. The impact will cause a massive dust plume that covers the entire Earth, shutting out the sun and causing a considerable rise in temperatures at the point of impact. This kind of event would lead to the loss of billions of lives, and much of the planet's biodiversity would be annihilated. However, experts believe that some living forms might survive even in the face of such a cataclysmic disaster. According to NASA scientists, it would take an asteroid a whopping 60 miles wide to eliminate all life on Earth. Together, a genuine historical example of an asteroid impact occurred on June 30, 1908, when a 40-meter asteroid slammed into the Tunguska area in Siberia. This hit damaged a wooded area similar to the size of London, distinguishing it as one of the most destructive asteroid impacts in modern history. Recognizing the potential hazards asteroids pose, the United Nations recognized June 30th as International Asteroid Day in 2016. This day attempts to raise awareness about the risk of Earth colliding with asteroids, which are countless celestial entities drifting in space. Scientists, astronauts, and celebrities join on Asteroid Day to highlight the hazards our planet faces from asteroids that cross Earth's course. These events underline the current vulnerability in our space defense systems against prospective asteroid strikes. Discussions on science fiction scenarios and potential answers take center stage in the face of prospective threats, emphasizing the necessity for continuing research and preparedness. Recognizing the magnitude of this threat, international experts and governments worldwide have chosen to begin a comprehensive global asteroid defense program. However, adequately defending against asteroids poses a formidable problem for various reasons. Asteroids are deadly and elusive, emerging suddenly or shifting their orbits due to cosmic events. In the worst-case situation, we only have weeks or months of warning before an oncoming disaster. To combat this, researchers globally constantly monitor all known asteroids and comets near Earth around the clock. Any slight alteration in orbit is painstakingly analyzed, and in crisis, NASA releases an asteroid warning. In the last 2 decades, there have been 3 such warnings. Fortunately, we just dodged tragedy each time, as heavenly bodies missed Earth by several tens of thousands of kilometers. However, relying on chance is not a viable strategy for the long term. Experts worldwide concur that in asteroid defense, there are only 2 possible approaches: violently moving the asteroids out of their orbit or towing them away. The DART mission aimed for Doros exemplified the first method. NASA launched DART in 2021. The mission's purpose was to crash the DART spacecraft into Doros, a near-Earth object, NEO, in order to test a revolutionary strategy for planetary protection. Should the kinetic collision be successful, Doros' orbit would be permanently modified, and it would slow down slightly. Indeed, even modest adjustments to an object's orbit over time can have enormous long-term implications. As indicated previously, Doros by itself does not harm humanity, but in principle we might identify a threat years before it reaches Earth and reroute it far enough away from us to miss us totally. Another prevailing theory suggests that black holes form from extreme density fluctuations of the infant cosmos that gradually accumulate mass through accretion. According to observations made by the James Webb Telescope, this theory might have some truth to it. The observations revealed the presence of supermassive black holes dating back just a few 100 million years after the Big Bang. This is a major shift in our understanding of black hole formation. It also suggests that black holes play a pivotal role in the early evolution of galaxies. Moreover, the JWST has uncovered the intricate interplay between supermassive black holes and the galaxies that host them. When matter, such as stars and gas, comes within the gravitational reach of a supermassive black hole, it undergoes a process called accretion. This forms a swirling disk of hot gas and dust known as an accretion disk. As matter falls into the black hole, it releases enormous amounts of energy in the form of radiation and powerful jets of particles. These jets of particles shape the surrounding environment and have a major impact on the growth of the galaxy. The influence of supermassive black holes extends beyond their immediate vicinity and can affect the formation of stars and the evolution of galaxies on cosmic scales. It is also noteworthy that the intense radiation and energetic outflows produced by these cosmic giants can heat the gas within galaxies. When these gases are heated up, the formation of new stars is inhibited, which can alter the overall structure of the galaxy. These outflows can also trigger the formation of stars in other regions of the galaxy. This means that there is a constant interplay of black holes and stellar birth. Beyond black holes and dark matter, the James Webb Telescope has revolutionized our understanding of star formation and the birth of planetary systems. By capturing images of stellar nurseries and protostellar disks, the telescope has provided unprecedented insights into the processes that govern the formation of stars and planets. At the center of our understanding of the universe, our world began with a Big Bang. This theory is the fundamental framework that unlocks the intricate timeline of our universe's evolution. According to this theory, there was a single point of inconceivable density and energy where the fabric of space and time was born approximately 13.8 billion years ago. This singular event marked the beginning of our universe as we know it. In a fraction of a second, this primordial ball of energy underwent a rapid expansion known as cosmic inflation. This rapid expansion gave birth to the fundamental building blocks of matter and energy. The universe became a seething, expanding sea of subatomic particles that eventually formed the first atoms. These atoms then aggregated into clouds of hydrogen and helium gas. Gravity then took hold, causing these clouds to collapse and form the first stars and galaxies. Over billions of years, these galaxies have continued to evolve and grow, forming the rich tapestry of structures that we observe in the universe today. The timeline of the universe is marked by key milestones, each offering a glimpse into the cosmic history. The timeline is marked by the formation of the first stars, the assembly of galaxies, and the formation of black holes. These celestial objects play a vital role in shaping the cosmos and driving its evolution. The study of these cosmic phenomena provides insights into the fundamental laws of physics and the origins of our universe. The timeline of the universe is marked by key milestones, each offering a glimpse into cosmic history. As the universe continued to expand and cool, the first galaxies began to form within a few hundred million years after the Big Bang. These early galaxies were small and irregular in shape, consisting primarily of young, massive stars that formed from the gravitational collapse of dense pockets of gas. The formation of stars within these galaxies marked another crucial phase in cosmic evolution. Stars are born when dense regions of gas and dust collapse under their own gravity, forming protostars that eventually ignite nuclear fusion in their cores. This process releases vast amounts of energy, which radiates into space and shapes the surrounding environment. The birth of stars not only illuminates the cosmos, but also enriches it with heavy elements forged in stellar cores and dispersed through supernova explosions. Over billions of years, galaxies continued to grow through mergers with other galaxies, interactions with neighboring structures, and ongoing star formation. These interactions led to the formation of more massive galaxies, including spiral galaxies like our own Milky Way and elliptical galaxies with older stellar populations. Each galaxy contains billions to trillions of stars, along with vast amounts of gas, dust, and dark matter. The evolution of galaxies is intricately linked to the presence of supermassive black holes at their centers. These black holes, which can contain the mass of millions to billions of suns, form through the accumulation of matter and gravitational collapse. As matter falls into the black hole's gravitational grip, it releases tremendous amounts of energy, producing bright jets and radiation that can be detected across vast distances. The influence of supermassive black holes extends far beyond their immediate surroundings. Their energetic outflows can heat the gas within galaxies, suppress star formation in certain regions, and influence the distribution of matter on cosmic scales. Understanding the role of black holes in galaxy evolution is a fundamental aspect of modern astrophysics and requires sophisticated telescopes like the James Webb Space Telescope to probe their mysteries. One of the revolutionary aspects of the James Webb Telescope is its ability to study galaxies in the early universe, providing a window into the cosmos's infancy. By observing galaxies that formed just a few 100 million years after the Big Bang, scientists can trace the evolution of cosmic structures and uncover the processes that shaped the universe's large-scale structure. The telescope's infrared capabilities are particularly well-suited for this task, allowing it to peer through cosmic dust clouds and observe faint signals from distant galaxies. These observations have already yielded surprising results, including the discovery of supermassive black holes in the early universe. Such findings challenge existing models of galaxy formation and provide new insights into the cosmic environments that existed billions of years ago. In addition to studying distant galaxies, the James Webb Telescope is poised to revolutionize our understanding of exoplanets, planets orbiting stars outside our solar system. By analyzing the atmospheres of these distant worlds, scientists hope to identify signatures of life, such as water vapor, oxygen, and methane. This search for biosignatures is driven by humanity's enduring quest to answer one of the most profound questions. Are we alone in the universe? The discovery of potentially habitable exoplanets would have profound implications for our understanding of life's origins and prevalence in the cosmos. It would also inform future space exploration missions aimed at studying these distant worlds up close and possibly detecting signs of extraterrestrial life. The James Webb Telescope's role in this endeavor is to lay the groundwork for these ambitious quests and expand the frontiers of human knowledge. Beyond its scientific achievements, the James Webb Space Telescope represents a triumph of international collaboration and technological innovation. It is a testament to humanity's enduring curiosity about the universe and our capacity to push the boundaries of exploration. The telescope's development involved contributions from scientists, engineers, and researchers from around the world, each bringing their expertise to bear on the complex challenges of space exploration. The telescope's journey from conception to launch spanned decades and required overcoming numerous technical and logistical hurdles. Its development involved designing and building cutting-edge instruments capable of withstanding the harsh conditions of space and delivering precise measurements of distant celestial objects. The successful deployment of the James Webb Telescope in December 2021 marked a milestone in human achievement and opened a new chapter in our quest to understand the cosmos. Looking ahead, the James Webb Telescope is expected to operate for at least a decade, providing astronomers with a wealth of data to analyze and interpret. Its observations will continue to shape our understanding of galaxy formation, star birth, planetary systems, and the fundamental physics governing the universe. Each new discovery made possible by the telescope's advanced capabilities will deepen our appreciation of the cosmos's complexity and beauty.